and I would like to welcome you to my presentation about a 0.037 square millimeters, 1 gigasample per second, 12-bit self-calibrated 40 nanometer CMOS DAC cell with SFDR more than 60 dB up to 200 megahertz and IMD3 less than minus 60 dBc up to 350 megahertz. This is work done together with Patrick Quinn. So it's all about small data converters which will enable massive arrays. And the motivation for this is that now today we have a lot of processing power in digital domain, but the world that we live in is still analog. And unavoidably we need the conversion from digital to analog in order to benefit from the advantages of digital domain. And we want to do more, and more comes with redundancy. And luckily the progress favors redundancy. For example, spatial selectivity in telecommunication. And spatial selectivity is something very much needed, for example, in 5G standards where phased arrays are needed. So 5G actually channels the information that is transmitted in a certain direction. And this is done by multiple antennas in a phased array. And if we want to control from digital domain in a very accurate way this beam, and if we want to have even more beams, so we have if we want to have multi-beam communication, we need to go to digital beamforming. And to go to digital beamforming means that from digital to antenna, this should be replicated in separate channels, which means that you have to use digital to analog conversion per antenna. And we are talking about 16 256 D2A converters in parallel. The problem is that if they are not integrated, so basically you use say a single chip per D2A converter, and then the integration is on PCB level, there will be some interconnection between the digital processor and the DAC, and this will be very, very expensive in both in terms of power but also the quality of the signal in terms of synchronization. These buses will be enormous. At high speed you have to use differential LVDS signaling, and you have to propagate the signal to up to certain distance. And if you use PCB and if you use DAC chips in a PCB, large arrays of them, they will occupy the area, so you have to propagate these signals to larger area. This will create a lot of problems with synchronization, but also will require a lot of power to drive at high speed these signals. So what you want is to put these D2A converters inside the digital processor. In order to be able to do this, you need first that each unit of these D2A converter cells is very small, extremely small, because the total area that they will occupy will multiply by the array factor. Another thing that you need is that each cell is very power efficient, because a single chip needs to handle all the power of the array. And in the same time, you want them to be high performance, still to meet the requirements, the tough requirements for wireless telecommunication. And this is a problem. So the problem with in this trade-off, the problem of combining high performance and small area is as follows. So high performance, first let's define high performance. What we understand by high performance is wide band, which means high sample rate, and high linearity. Wideband directly prohibits oversampling, so you cannot use digital sigma delta. And this leaves us with the standard architecture for D2A converters, which is a flash architecture. And now the other requirement about high linearity. High linearity actually requires small errors. So if we think in D2A converters about small errors, we think immediately about unary architectures. The problem there is of course the area. So if we want to minimize the area, we think about binary D2A converters. But binary D2A converters feature a lot of errors, and especially the mid-transition errors, which generate a lot of harmonic distortion. And this applies to amplitude errors and timing errors for binary architectures. So this means that if we want to enable massive integration of D2A cells, and we want them to be small, power efficient, and fast, we have to enable binary D2A converters with small errors. And the way to do this is through calibration. Calibrating the errors of binary D2A converter is key to small area high performance and hence to massive arrays. And this is the main hypothesis of this work and the main topic of this presentation. So this brings me to the contents of my presentation today. I'll continue with binary and unary current steering digital to analog converters and explore the trade-off. Then I'll introduce the calibration for binary converters, present our proof of concept a small area 12-bit DA converter cell in 40 nanometer CMOS, its massive integration into an array of 16. I'll show some measurement results, and in the end I'll draw conclusions.